Hi, this is the fourth video in the data section. This is about mean and variance. In the previous video, we talked about other measures of central tendency and dispersion, basically the median and either the range or the interquartile range, and so which is useful in certain circumstances. In other circumstances, we're interested in the mean and the variance. And that's what this is about. So let's just be clear what we're talking about. I mean, typically this is all about populations. Populations are usually large sets of data, so large that we tend not to be able to measure them, and what we do is we draw a sample in order to help us estimate the parameters. When we say parameters, let's just think at the moment about mean, and well, we're measuring dispersion by variance, so that's what we tend to be referring to. Okay, so we tend to use Greek letters for measuring the parameters of populations, and our own sort of ordinary letters for samples. Now, a sample we might use the sample in order to estimate the population, or we might be interested in the parameters of the sample on its own. And there is a slight difference, which I'm going to come to. So, well, let's have a look. What do we have lots of numbers, basically. That's the data we've selected. We usually call these, let's say, X. We can apply any letters, and if we number them, then there will be X1 up to X. If we have N of them, it would be XN. So we denote them like this. And if we want to take the mean, then we basically add them all up. That's what this means, and divide by the count of them, and that gives us the mean of that set of data, which we denote by X with this bar over the top, X bar. The variance, so this is the measure of spread, and what we're actually looking is we want to know how far around the mean the data is kind of spread out. So what we do is we subtract the mean from each data item. But if we were just to add those up, then obviously the mean lies somewhere in the middle. So the difference would be, there would be positives and negatives in there, and if we added all those up, we get something which is pretty meaningless, possibly something close to zero. So what we do is we take the square, which is always a positive number, and then we take the mean by dividing by the count, and that gives us a measure of spread. Okay, so now I've used the Greek letter here. Here I've used S, small s squared. Now this is assuming basically we're just calculating the variance of all the data. So this is based on all the x's, all the numbers that we've gathered. So this actually is just a little bit of maths applied to this. And actually this takes it slightly further. So this is what we're sort of interested in here, is the variance is this expression, which we can think of as being the mean of the squares. Well, if we square each item and add them all together, that's what this is. And then we take the mean, divide by the count, that's the mean of the squares, minus, now this is the mean, so the square of the mean means, but the square of the mean. So the variance we can think of as being the mean of the squares minus the square of the mean, and this form actually is what we normally use. We might revert to doing it like this if we use a spreadsheet or something like that, but that's what that's normally what we tend to use. It's the most convenient for most purposes. Now, I mentioned standard deviation here. So standard deviation is the square root of the variance. So why would that be of interest to us? Well, of course, if all our data is in meters, for instance, then when we calculate this spread, we actually, because we're squaring it, we effectively have something which is square meters. And that's not very convenient for a lot of purposes. We want the measure of spread to be in the same units as the actual data. So we take the square root. That brings our square meters back to meters. So that's why we do that. Just another little thing just to point out is that sometimes in some text you'll see a large S used, usually written like this, maybe SXX or a couple of letters down there. It's not the same as this. It basically is a sort of intermediate stage in calculating this effectively before we divide by n. Essentially, so so we won't need this. We don't tend to use this. Certainly not at in these videos. And but just to mention, if at some point you see a large S with these suffixes, then be aware that it has a slightly different meaning. Okay, so let's go on and have a look at an example. Okay, so here's a set of data. We basically want to find the mean and the variance of it. And well, we could do the calculation, but calculator does it for us. So let's assume that we're doing this. So we're going to go into our ClassWiz calculator, which is the standard for most people these days doing exams in the UK. And yeah, we just go through this little sequence here. We enter the data in this list here. We take option and one variable calc, and it comes out with all this set of stuff for us here. And so this is on the first page. If we use our down arrow, we'll see all this stuff. So I'll just pick out the main things that we're interested in. That's our X bar that we just talked about. It's got the sum of the squares there as well, which I referred to. This is the variance of the data, the variance of this set of numbers. Okay. And then if we would take the square root, we would get this. It's standard deviation. Two tend to go together. This S squared X is actually well, it's an estimator. So if this data came from some larger population and we wanted to estimate the variance of the population from which all this came, then we would this is what we would be interested in. It's slightly higher because our process of calculating the variance, this is assuming that it's based on using the X bar. So we're then actually going in and subtracting X bar from each one of these, squaring it, adding them all up. That actually gives us a biased result because the differences are based on the X bar, which is based on the data. So we actually have a bit less data available than we think we have. So in order to adjust for that, and this is mathematically rigorous and also can be shown, if you do it on a computer, you can actually show it to be true with simulation and so on. Yeah, basically it's a bit higher. How much higher? Well, what we're effectively doing is in this calculation here, instead of dividing by n, we're dividing by n minus 1. It sounds like a trick, but as I say, it is actually mathematically rigorous. So we just have to be clear when we're looking at data, whether we're interested in the variance of that data or whether that data, we're using that data in order to estimate parameters from which the data has come. So yeah, so that's the point of that. So yeah, so the calculator does all this stuff for us, and which is nice and easy for us. Okay, let's have a look at this example here. Calf coffee sold in packets. Seller measures the masses of the contents of a random sample of 90 packets of calf coffee from her stock. Results are shown in the table below. So this is the data. I mean, we've collected all these 90, but we've categorized it into these weight categories here, each of which has a midpoint. So 242.5 is this midpoint. And so there are 8 coffees that fall into this category. Having categorized it all, we can sort of imagine that we haven't got our original data anymore. But we can still draw conclusions from this. So it goes on to say, calculate the mean and the variance of the sample. So I'm just looking at the data for this 90 packets. Okay, so what we are doing, if we want the mean, then basically we want to add up all the weights of all 90, divide by 90, and that will give us our mean. We haven't actually got the individual ones, so what we're assuming is that all 8 of these have this mid value here. Instead, they've used y's here and the x's down here, but assume they're just the same thing. So what we're doing really is assuming that all these 8 are spread evenly across here. It's a reasonable assumption. You know, overall, they won't be far away. So if we want to get back to the total weight for those 8, then we're just going to multiply by this mean, this midpoint. We're assuming it's the mean of the ones of those 8. So we multiply it out, we get that, and then we do the same thing for all the other rows. We add all those up, and that 22,535.5 is, well, it's an estimate, but it's what we are taking to be the total mass of these 90. Okay, so so the mean, yeah, it's just it's that 22,535.5 divided by the counts. That's going to give us a mean of 250.39 well, grams, in fact. And the variance is going to be, the variance of this data is going to be the mean of the squares minus the square of the mean. So now we're told that what the sum of what the squares is, the mean of the squares. So that's the sum of the squares. So yeah, so if we squared each of those, multiplied it by that, and then did it for all of them, and then added them all together, this is what we would get. So the mean of the squares, that's what that is, minus the square of the mean, which we've just calculated here. Work that through, that's 17.9 to 1 decimal place. Put a note on there saying it's an estimate because it uses these midpoints rather than the actual values. Okay, and then it goes on to say, estimate the variance of the mass of a pack of coffee. Right, so now what we're saying is there is this bigger population of coffee packets that some of them which haven't maybe not been produced yet. Most of them, I don't know. So this is why we're now using this data in order to estimate the parameters of a population from which the sample is drawn. Okay, so well, our estimate of the mean of the population would be the same. That doesn't change, but the variance we do have to make this what is effectively an adjustment, because we didn't divide by n-1, did we? We divided by n. And so we have to make this correction here. So 17.9 is the variance of our data. 18.1, therefore, is our estimate of the variance of the population. So that is something to bear in mind. Now, why this is the case? It does seem rather counterintuitive, but we can we'll provide an illustration as to why this is the case in another video. Okay, so that's good. Right, another thing. Well, I missed this out first time on this question, but let's just have a look at this, because this is something that does crop up. And this is going back to medians, and it does say use linear interpolation to estimate the median mass of the contents of a packet of calf coffee to 1 decimal place. I've got it to 3. Bonus. Okay, so what are we doing here? Well, what we want. So we got 90. So the median is actually going to be, well, we haven't got a middle one, have we? We got, it's an even number. So what we kind of want is the 45th and 46th, and then we'll just kind of, you know, take the middle point. So we have to estimate where the 45th and 46th ones are. Right, well, we've got 23 in these two categories. So the 45th would be the 22nd out of this 35. And then the 23rd, so I'm on the 22nd. So we're the 22nd and the 23rd in that category. So have a look. If we imagine drawing this thing, this is this middle section here. If we had it here, we've got 35 in this group. We're assuming they're all spread out evenly, and so the width, the distance between, because this is 4 wide here between the 252 and the 248. So each of these gaps would be 4 35ths. Now, just to be that, now I might be getting a little bit kind of picky here, but the way I've done this is I've sort of said, well, they start part way up, because remember we've got a category further down here, and so for assuming that they're spread evenly, there won't be anything at this node. There won't be anything actually at 248. The first one will start half a width up, and the last one finishes half a width from the end. So if we add all those lengths, we've got all these 4 35ths, and there's a couple of 2 35ths, one at each end, and that will fill up your total width of 4. So okay, I'm perhaps being a little bit more nitty-picky than you actually need to be. At the end of the day, it just says an estimate, so you can probably simplify it a little bit. Anyway, this is the way I've done it. So each gap is 4 35ths, and first and last are second 35ths. And we want the 22nd and the 23rd in this category. So the 45th is at, well, as our starting point, and then we add on that first gap there, plus 21 lots, because that gives us to the first. So we want to get another 22 along, another 21 along. So that would be 21 4 35ths. And then the 46 would be similar, but of course we've got another one to go there. So if we work that out, we get these two numbers, and then we want to be in the midpoint of these two, and that's going to give us this. I've got 250.514, 250.5 to 1 decimal place. Does that make sense? Yeah, it does. You know, we're going to be on the right side of the midpoint, aren't we? Because we're at 22, 23 out of 35. Yeah. Okay, so it's kind of it looks plausible, doesn't it? So that is linear interpolation. I say, you know, I've gone a little bit more detail perhaps than necessary when we're looking at this. You know, we could just sort of say, well, let's just go, we want 22.5 35ths of this gap. Be easier to do, wouldn't it, really? But anyway, that's what I've done. A couple of other things. The height of sweet pea plants grown in nursery is a random variable. A random sample of 50 plants is measured and found to have a mean height of 1.72 and a variance of 0.0967 meters squared. Calculate an unbiased estimate for the population variance. Right, okay, so the biased estimate is going to be low. We're going to have to correct for that by multiplying by 50 divided by, well, n divided by n minus 1, and that's going to give us this 0.0987. And finally, the weight of fat in a digestive biscuit is known to be normally distributed. Not actually relevant for this. Pat conducted an experiment in which he measured the weight of fat X in each of a random sample of 10 digestive biscuits with the following results. So that's the sum of the X's, and that's the sum of the sum of the square of the differences. Use this information to calculate estimates of the mean and standard deviation of digestive biscuits. Well, that's okay. Our estimates of the mean of all digestive biscuits is going to be this 31.9 divided by the count of our sample. The estimate of sigma squared, however, is going to be 1 over n minus 1, n being 10, 1 over n minus 1 being 1/9 of this sum of the squares of the differences, 1.849, and that's going to give us this figure of 0.205 to 3 decimal places. So that is what we are estimating the variance of digestive biscuits fat to be. Okay, so that is that. Hopefully that's been useful, and